everyone, and welcome back. My name is Mr. Koval, and in this video, we're going to be going over how to determine which of a given set of substances exhibits the given property being asked for. So let's get into this. Okay, so in this problem, they're asking in each of the following groups of substances, pick the one that has the given property and justify your answer. So in all of these cases, it's going to come down to what kind of intermolecular force or attractive forces that are happening inside the or among the particles of the substance, and which ones have greater strength, right? So just let's recap or summarize what these attractive forces are. So here I have written down here intermolecular forces or IMF, and I've got 6 of them. So the first one is LDF, your London dispersion forces. That applies to molecules mainly. This will be the predominant force for any molecule or substance that is nonpolar, right? So this is the weakest of the intermolecular forces. I want to state that all substances, whether polar or nonpolar, is going to have London dispersion forces. However, if you are nonpolar, this is the only force that you have. This is the only intermolecular force you have. So this is going to be the predominant force if you're nonpolar. The next one is dipole interactions. If you are a polar molecule, you're going to have that as your predominant intermolecular force. You're going to have LDF, but you're also going to have dipole. And so this is where you have a separation of charge in your molecule or in your substance, such that you have a positive side and a negative side. So that's going to allow for attractions between the molecules that are stronger. So your dipole interactions are going to be stronger than your LDF. Again, your polar molecules are going to have LDF, London dispersion forces, and dipole, but dipole will be the predominant force. It's the stronger type of intermolecular force. And then after dipole, you have hydrogen bonding, or H bonding for short. This applies to the special polar molecules that have hydrogen in it, but that hydrogen atom must be bonded to a nitrogen, an oxygen, or a fluorine atom. That has to be the case. In order to have hydrogen bonding. So if the substance or the molecule has a hydrogen atom bonded to an oxygen, a nitrogen, or a fluorine, then that substance will exhibit hydrogen bonding. But again, let's not forget that because this is a special polar molecule, it's also going to have dipole and London dispersion forces, but hydrogen bonding will be the predominant force because it's the stronger type of the 3. So technically, these are the these are the intermolecular forces. Now I have 3 others that are kind of intermolecular forces. They're not quite intermolecular forces. They're more like bulk forces or bulk properties. They kind of are in between your intermolecular forces and your intramolecular forces. And that is your metallic bonding. So this is the bonding that you see in metals. Then you have your ionic bonding. That's going to be your ionic substances that have plus and minus ions, your positive and negative ions, cations and anions in there. And then you've got your network covalent solid. That would be like any covalent substance that has a network of atoms that are kind of bonded together in some mesh or system of bonding. So in these, it's hard to pick out any individual particle or unit, right? So metallic is usually going to be a sea of electrons, right? So you have positive nuclei and a sea of electrons. So it's hard to pick out the unit. Maybe the unit might be the atoms itself. Each individual atom is a unit, but they're kind of tied together by a sea of electrons. Ionic substances, again, it's hard to pick out what the unit is. We don't really talk about molecules in ionic substances. We use formula units as a description, and that's because you really can't pick out a particular particle, right? And then the same thing for the network covalent solid. So these are going to have much stronger interactions or attractive forces than these here. So this would be the order. So metallic is a weaker force, followed by ionic bonding, and then your network covalent bonding is going to be the strongest force. Okay, so that's a good overview, a summary of the different interactions that you can happen, and that's going to that's going to help us determine which of the given molecules or substances will have the particular, how should I say, property that we're being asked to look at. Now, how does this relate to these? Well, I'll go over them one by one, and I'll explain as I go along. So let's go ahead and start with A. So A says, oh, it has highest boiling point, right? Okay, excuse me. And we're given these three substances. So what determines boiling point? Well, the boiling point is the point or temperature at which the liquid begins to transform into the gas phase. So you get a change from liquid to gas. So you get that transformation happening, that phase change is occurring. So in order for that to happen, the intermolecular forces of the particles of that substance have to be overcome such that they separate from each other and they're able to leave and become gaseous particles, right? So how does this relate to the intermolecular forces? Well, the stronger that force, the more energy you have to put in to overcome that force to separate them, and therefore the boiling point is going to have to be higher. You got to put more energy in, so you got to raise that temperature higher in order to get it to phase change from liquid to gas. So the stronger the intermolecular force, the higher the boiling point needs to be in order to get that phase change, right? So we have to look at which one of these is going to have the strongest intermolecular forces or the stronger attractive forces that's going to need to be overcome. That one's going to have the highest boiling point. So here we have Hg, mercury, that's a metal, right? So if we look at metals, right, metallic bonding is here. We have NaCl, that's ionic, sodium plus Cl minus, so that's ionic. We have that here, that's going to be stronger. And then we have N2 gas, right? So that is a nonpolar molecule, so that's going to be over here, LDF forces. So given the type of interaction, the type of attractive force, we would have to say that the ionic substance is going to have the stronger attractive forces that must have the highest boiling point, because you need to put the most energy into that one to overcome the attractive forces to get that phase change from liquid to gas. So that's the answer to this one. So NaCl would have the highest boiling point. Let's move on to the next one, B, smallest surface tension. Now, what is surface tension? Technically, surface tension is the amount of energy that it takes to separate the particles in the surface of your substance, right? So if you have your surface here, you've got molecules or particles here that are attracted to each other, and that's keeping the surface together. That's keeping it as less as possible. So they're attracting each other as much as possible to decrease the amount of surface that's there. So if you're going to break the surface, if you're going to break that surface tension or increase the surface, right? If I'm going to increase the surface here, right? If I'm going to cause these molecules to break apart and increase the surface, that's going to take a certain amount of energy because I've got to break those particles apart to make more room to increase the surface area. And so, in order, the energy that's required to do that is called the surface tension, right? So, again, that's the amount of energy you need to put in is going to depend on how strong those interactions are between the particles on the surface, right? So, the stronger the attractive force, the harder it's going to be to pull them apart to increase the surface area. And so, that's going to be a measure of surface tension. So, stronger attractive forces means higher surface tension. So we're asked which one has the smallest surface tension. So we're looking for the substance that has the weakest interactions, the weakest attractive forces. So if we look at water, H2O, that has hydrogen that's bonded to oxygen, that's going to have hydrogen bonding. So that's going to be here on our scale of strength of the intermolecular forces or attractive forces. Okay, so we got hydrogen bonding for water. Here we have CH3CN. So there's no hydrogen bonded to nitrogen here. The hydrogens are bonded to carbon, so no hydrogen bonding there. We do have nitrogen and carbon bonded together. So that's going to be a difference in electronegativity. So there's going to be polarity there. So that's going to give dipole-dipole interactions. So we have dipole-dipole interactions here, but that's going to be less stronger. That's going to be weaker than the hydrogen bonding, right? Because again, remember, we're looking for smallest surface area. So we're looking for weakest interactions, weakest attractive forces. And then we have CH3OH. Here we have hydrogen bonded to oxygen, so that's going to be hydrogen bonding. So we have this one. This is your methanol. Methanol and water both exhibit hydrogen bonding, so that's going to be a stronger attractive force. And then we have, this has just the dipole-dipole. That's so we would expect that to have weaker attractive interactions, weaker attractions. And so therefore we would suspect that this one would have the smallest surface tension. So that means that CH3CN is going to have the smallest surface tension. Okay, next we have lowest freezing point. Okay, how does a freezing point relate to the attractive forces? Well, again, how do you get things to freeze, right? Freezing is, again, a phase change going from your liquid to solid, right? So, again, how do you get things to freeze or become a solid? Well, you've got to get those interactions to start to work on each other, pulling the particles together into place so that they're kind of locked into place. But you also have to deal with the speed of the molecule. So if you've got a liquid, those particles are moving around at various speeds, right? So they're still attracted to each other, right? That's what keeps them close together in a liquid phase, right? But they're not so, how should I say? They're still moving around fast enough such that the attractive forces can't lock them into place. So they're moving too fast, so they can't be locked into place as a solid, but they're not moving fast enough, or they don't have enough energy in them in order to completely remove themselves and overcome those attractive forces that are there and become a gas, right? So we want the liquid to become a solid. Well, how is that going to happen? Well, you got to take energy out of the particles, slow them down, right? Lower the temperature, right? So if you take energy out, right? Remember, temperature is a measure of the average kinetic energy of the particles in the substance, and kinetic energies are related to the average speed of the particles. So if you can take the energy out of the substance, right, that would lower the temperature, right? And if you lower the temperature, right, if the particles are moving slower, what happens? That gives, if the particles are moving slow enough, then that will give the attractive forces the opportunity to attract them, lock them into place, and then it starts to solidify. So the stronger the attractive force that you have between the particles, then the less energy you need to remove in order to get them to lock into place. So the stronger those attractive forces, it's easier to get them into place without having to lower the temperature, right? So, but if those attractive forces are already quite weak to begin with, then you're going to have to slow them down even more, so that way that those weak attractive forces can eventually attract them strong enough so that we can lock them into place. So the upshot here is that the weaker the attractive force, the lower you have to lower the energy or the temperature in order to get them to slow down enough so that those attractive forces can then attract them strong enough to lock them into place and start to solidify. So in this question here, we're looking for the lowest freezing point. So which substance do you have to lower the temperature the most in order to get them to solidify? Well, that's going to be the substance with the weakest attractive forces. So here we have hydrogen, H2, that is a nonpolar molecule. So that's going to have London dispersion forces. Okay. So that is pretty weak. CH4, that also is a nonpolar molecule. So that's also going to have LDF. So that's going to be weak. And then we have CO, carbon monoxide. That's going to have a difference in electronegativity. Oxygen is pretty electronegative compared to carbon. That's going to have a polarity to it. So we're going to have dipole-dipole. So that's going to be stronger than the LDF, right? So that one we can eliminate. But what about these two? They both have LDF, London dispersion forces, right? So, and that's the weakest of the two. So how do we determine which one's going to be the lowest freezing point? Well, this is where the size or molecular mass or molar mass of the substance comes in. What we need to remember is when it comes to London dispersion forces, the size of the molecule matters, right? So the larger the molecule, the more electron density you have, and London dispersion forces are dependent upon or arise from the polarizability of the molecule, which is based on how much electron density you have. The more electron density you have, the more fluctuation, the larger the fluctuation of the electron density is, and therefore the stronger the London dispersion forces. So larger molecules are going to have more electrons, and therefore, because they have more electrons, they're going to be more polarizable and therefore give rise to more or higher or stronger London dispersion forces. So in this case, the smaller of these two is going to have the weaker London dispersion forces, and that's going to be your hydrogen molecule, your H2. So hydrogen molecule H2, we would expect to have the lowest freezing point, right? Okay, let's go on to D. Smallest vapor pressure at 25 degrees. So what is vapor pressure? How is that measured? Vapor pressure is defined as the pressure due to the vapor of a substance in a closed container. So here we are looking at a container that's closed. We have a certain substance in the container. That substance is going to give rise to vapor particles, right? So you would expect some of those particles to go from one phase into the vapor phase. So you've got these gas particles moving around in the gas phase above the surface of your substance. And so those particles are going to give rise to a pressure, right? Because the particles are bouncing around in the container. They're hitting up against each other. They're hitting up against the container, putting pressure on the container when they collide with the side of the container. And so the more particles you have in that situation, and this, again, we're looking at something that's at equilibrium. So there's a dynamic equilibrium here. So once the equilibrium is established in the closed container, right, that's going to have a certain pressure to it based on the collisions of the particles in the gas phase. Okay, so how is that related to the intermolecular forces? Well, you can imagine that the stronger the intermolecular forces are, the harder it is for those particles to break free and become gas particles, right? Break free. So the weaker the attractive forces in the, between the particles, right? The easier it is for those particles to free themselves from whatever phase they're in into the gas phase. So you would expect more particles to be in the gas phase for substances that have weaker intermolecular forces. So the weaker the intermolecular force, the easier it is for those particles to escape into the gas phase. The more particles you're going to have in the gas phase at equilibrium, and the more particles you have in gas phase means more collisions on the surface of the container, which means more vapor pressure, higher vapor pressure. Here we're looking for the smallest vapor pressure. So the smallest vapor pressure means you're going to have the least amount of particles in the gas phase, which means that the intermolecular force or the attractive forces between the particles is going to be the highest. So we're looking for the highest attractive forces in our substances. So here we have Si2. This is silicon dioxide. This is a network solid or covalent network solid. So this is network solid that's going to have the strongest attractive forces. So far, so good. This is silicon dioxide is the same as sand. We see this in sand. Also, since glass is made of sand, this is probably found in glass too. CO2, carbon dioxide. This is a nonpolar molecule. So that's going to have London dispersion forces. That's going to have the weakest attractive forces. And then we have water, which is hydrogen bonding. So that's going to be in between carbon dioxide and silicon dioxide. So of the three, silicon dioxide is going to have the strongest attractive forces because it is a network solid. And so therefore, we would expect that to definitely have the smallest vapor pressure at 25 degrees Celsius. And we know, and that makes sense because silicon dioxide, as I said, is sand. That's a solid at room temperature. Carbon dioxide is a gas at room temperature, and water is a liquid at room temperature, which is about 25 degrees, right? Okay, next we have strongest hydrogen bonding. So again, in order to exhibit hydrogen bonding, you must have hydrogen bonded to either an oxygen, nitrogen, or fluorine. If you do not have hydrogen bonded to any of those three atoms in your molecule, you don't have hydrogen bonding. So let's look at what we're given. So NH3, we have three hydrogens bonded to nitrogen, so that indeed can exhibit hydrogen bonding. Here we have phosphorus. We have three hydrogens bonded to phosphorus. The formula looks very similar, but notice here that it has phosphorus. So the hydrogens are bonded to phosphorus. They're not bonded to nitrogen or oxygen or fluorine, so this does not exhibit hydrogen bonding. And the same goes for antimony trihydride, right? So this is also not going to exhibit hydrogen bonding. So the only one that has hydrogen bonding is NH3. So obviously that's going to be the strongest hydrogen bonding. Next we have greatest heat of vaporization. What is the heat of vaporization? The heat of vaporization is the amount of heat it takes to vaporize your substance, meaning the amount of heat it takes to go from a liquid to a gas. Okay, so again, stronger attractive forces means it takes energy to overcome those forces in order to have the phase change. So greatest heat of vaporization is the one that has the greatest amount of heat needed to vaporize or have the substance go from liquid to gas. So we're looking for the substance with the strongest intermolecular forces or attractive forces. And so we have HF, HCl, HBr, HI. You'll see that HF here we have hydrogen bonded to fluorine. That's going to exhibit hydrogen bonding. So we have hydrogen bonding here. The rest of these have hydrogen bonded to something other than oxygen, fluorine, or nitrogen. So these are not going to exhibit hydrogen bonding, but they are polar, so they have dipole-dipole interactions. So we have dipole-dipole, right? These guys all have exhibit dipole-dipole, but as you go down the group in a periodic table, the chlorine, bromine, iodine, they are getting larger. So you have larger atoms, and so the distance between them is going to grow. The electronegativity is decreasing. So as you go down, the dipole interactions are going to get weaker, right? But as you go down, the atoms are getting larger. So your London dispersion forces are going to get stronger because the size of them is going to be larger. So there's kind of a play in your dipole-dipole versus your London dispersion forces. So there's that kind of thing going on. But be that as it may, HF exhibits hydrogen bonding, which is the strongest. Oops. Sorry about that. As I was saying, HF has hydrogen bonding, which is the strongest of the three. So HF would be expected to have the greatest heat of vaporization. And last but not least, we have the smallest enthalpy of fusion. What is the enthalpy of fusion? Enthalpy is another word for heat. So we're looking for the smallest heat or smallest enthalpy of fusion. Fusion is a word. It just means melting. So we're looking at the smallest heat of melting. What is that? That means that we're looking at the substance. We want to find the substance that has the smallest, that requires the smallest amount of energy in order to get your substance to melt or do a phase change from solid to liquid. So which one is going to require the smallest amount of energy to get it to melt? And again, that's related to the strength of the intermolecular forces or the attractive forces between the particles, right? So the stronger the attractive forces between the particles, the more energy you need to put into it to get those to kind of overcome those attractive forces and start to move and get that extra freedom or degrees of freedom of motion. And so that's going to take more energy, right? So stronger attractive forces requires more energy, and that means that the enthalpy of fusion is going to be greater, but we want the weakest or smallest enthalpy of fusion. So we want to find the substance with the weakest attractive forces, because the weaker the attractive forces, then you don't need as much energy to overcome those forces to get them to move more and start to melt. So which one is going to have the weakest forces? Let's see. Again, we have water. That's going to have your hydrogen bonding. So those are pretty strong. We have carbon dioxide. That's going to be a non-polar molecule. So that's going to only have your LDF or your London dispersion forces. So that's going to be the weakest here. MgO, that's going to have your ionic substance. So MgO is ionic. We have magnesium and oxide ions, and then we have lithium oxide that's also ionic. So that's going to be over here. So those are going to be pretty strong, right? So again, we're looking for the smallest enthalpy, which means that we want to find the weakest forces, and that would be carbon dioxide. So carbon dioxide is non-polar, therefore the only attractive force it has is your London dispersion forces. So that's going to have the smallest enthalpy of fusion. And we know that because CO2 is a gas already at room temperature. Water is a liquid at room temperature, and these are solids at room temperature. So obviously, carbon dioxide, it doesn't take much to get carbon dioxide to melt, right? So again, solid carbon dioxide is what we know is called dry ice. So that's solid carbon dioxide. And the thing we know about dry ice, if you've ever experienced working with dry ice, is that it sublimates. Sublimating is where the substance does a phase change, going from the solid phase directly into the gas phase. So it passes the liquid phase, it skips over the liquid phase and just goes directly into the gas phase. And that's expected because, of course, carbon dioxide has very weak attractive forces. Okay, if we had to choose between these two, like which one of these is going to have the strongest attractive forces, you would look at the charges. You notice here they both have oxygen. Oxygen has a -2. But if you look at lithium, lithium has a +1 charge. Magnesium has a 2+ charge. The higher the attractive charges, right, the stronger they're going to be attracted to each other. So if I had to choose between these two, this one I would say has the stronger attractive forces. But you weren't asked about that. But I thought I'd throw that in as a freebie. Okay, that's it for the video. I hope this was helpful. If this was helpful in any way, if you enjoyed the video, then please like the video, share the video, hit that like button somewhere over here. Also, do me a favor, subscribe to the channel, my channel. Do it now. Also, make sure that you click that notification bell. When you do, click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a problem or question you need help with, or if you have a topic you would like me to cover, put that down below. I would love to do that for you. Thanks for joining me and have a great day.